So look at the two probabilities. That's what make a difference. So the probability a mosquito is a vector is the quotient of the number of vector to the total number of mosquitoes. That makes sense, a simple probability model. So if you have 1,000,000 mosquitoes, 1,000 of vector, then the probability of the mosquito is a vector is 1,000 over 1,000,000. And then that will be 0.001. That makes sense, right? And similarly, the probability of the human is a host equal to total hosts of a human being divided by the total human population. So that also makes sense. Now, number 12 is another trivial. The whole human equal to uninfected human plus the human host plus the human immune. That's just like the number 5. The total mosquito equal to uninfected mosquito times the vector plus the vector. Now here's the conceptual model, the map of the mosquitoes. When we deal with the mosquito, we have 2 unknown variables, stocks. And for the uninfected mosquito, there's a birth, which equals the birth rate times total mosquitoes, and the death, and just the death rate times the population. For the vector, the death rate is the same, equal the mosquito death rate times the population for vector. Easy part. The real interesting part is this piece. That's when the uninfected mosquitoes become a vector. So how this happened? It happened because it have to bite a human being, and the human being have to be a host, and then this transition in the equation 9, if you remember, equal the total population of uninfected times the probability of beating the human, and times the probability the human was beaten is a host. All right, so we got this mosquito model, and now we look at both human population model and the mosquito models. Now I ask you a question. You got to think about it seriously. What's the connection between the two submodels? If you don't understand this, you don't make any sense for this new disease spread model. It's just like the old one. But once you understand the connection between the two submodels, then everything will make sense. Well, remember, this is not like our previous population model. A mosquito won't become a human, human won't become a mosquito. There's no direction population flow between the two species. The only thing connected then is the disease. When the mosquito bite a human, and when the mosquito bite a human, when this spread the disease. And to answer that connection, you really need to go back into the original diagram. So here. So first, this human must be a host. Only the host has this merozoites. The merozoites are the matured sporazorites. That's the number one. That's why the probability of the human is a host is important. Second, for the mosquito, it must be bitten the human. So the real connection is the mosquito bites the human host. And the first bite, you bite the host, and then develop the disease in the mosquito. The second bite an uninfected human. And if you bite this is uninfected, and then you change this uninfected human into another host. That's how the disease spread. In another word, the disease spread by the mosquito as a vector. You need the same mosquito first bite the host and second bite an uninfected. And if you understand this fundamental problem, now you can try to answer my question. Where's the connection between the two submodels? Now we can think about, in both models, which parameters. We know the variable will not share each other because the population won't change from mosquito to human, human don't change to mosquito. The real matter is this, the probability of beating. That is shared by both the human and the mosquito because it's a binary relationship when the mosquito bites a human. And the second is this, the probability of the human is a host. And that also affects both. Because if a mosquito does not bite a host, that matter. So you understand this two, not only in the human model, also in the mosquito model. Let me see, in the mosquito. Okay, that's the human model. Let's go to the mosquito model. In the mosquito model, let's look where you use that. See? The probability the human is a host, that's here. And the probability to bite a human is right here. So that two parameters shared by both submodels, that's the connection. And that connection is exactly reflected in this bite and this bite, because the probability of bites and the probability the bite is the host, and then this bite need to bite the uninfected. That's the connection. So the new knowledge for today's model is to really connect the two models, and then you can really figure out a strategy how to cure and just like Bill Gates Foundation said, eradicate the disease. So what triggered the population transfer from uninfected to a host, a vector bite the uninfected human, and then an infected mosquito bite the host. That's what matters, as we pointed in the procedure. Hence, the connection between that is the two probabilities. The probability of a vector, probability is a host, actually 3, the probability of mosquito bite. So another one, the probability of mosquito bites human. So that 3 probability is what you are going to try to reduce if we wanted to prevent the disease malaria spread.